Okay, so hi, welcome everybody. We are very happy to have today Jiashen Zhang with us, who is a PhD student in the Department of Computer Science at the University of Electronic Science and Technology of China, and who is specializing in temporal knowledge graphs and dynamic graph learning. And he's currently visiting Yale University, where working with Rex Ying on using large language models for temporal graphs and temporal knowledge reasoning. He's also recognized as a rising star in scientific research by UESTC. And today he will present DTGB, a comprehensive benchmark for dynamic text attributed graphs. And with this, I hand over the mic to you. Thank you for presenting.
Okay, thank you. So today I'm gonna introduce my recent work, accepted by Europe's 2024 Dataset and Benchmark Track, DTGB, a comprehensive benchmark for dynamic text attributed graphs. As we all know, dynamic graphs are essential for modeling a wide range of real-world systems, such as e-commerce, social networks, and knowledge graphs. In those dynamic graphs, nodes and edges are typically associated with text attributes. For example, in e-commerce graphs, items contains its text descriptions and time-annotated edges representing user reviews. Similarly, temporal graphs represent the sequential interaction among real-world entities through textual relations. And the exploration of learning methods applied to these dynamic text attribute graphs is important to various real-world applications, such as explainable recommendation or social analysis. Despite the urgent usage of such time-evolving and text attribution graph, datasets tolerated to this aspect are still unexplored. Previous works for dynamic graph learning have proposed many datasets describing the temporal interactions across different domains, such as MOOC and Last.fm. However, these datasets often lack edge categories and only contain statistical features from raw attributes, lacking the raw text descriptions. Some of them also suffer from small scale, which cannot sufficiently describe the complex interactions of real-world evolving networks. Moreover, most existing dynamic graph datasets lack reasonable temporal segmentation and aggregation, making their edge distribution quite sparse in the time dimension, such as Last.fm, and thus these datasets are more likely to be streaming graphs. This brings challenges to investigate the structure dependency and evolution for dynamic graphs. Some of graphs in real world actually have text attributes, such as Cora, but existing datasets either ignore these attributes or only provide the low-dimensional feature based on the text, such as bag of words based on the text descriptions. Recently, some text attribute graph datasets with rich raw text has been proposed, such as CS TAG datasets. However, these datasets oversimplify the involving interactions in the real world by representing them as static graphs, and they also neglect the text description and labels on edges, and which limits their sufficient describing of real world interactions. Uh, in summary, existing datasets have three main limitations. Firstly, they lack raw text description of both nodes and edges, and they lack a reasonable time segmentation, and they lack auxiliary labels. So these limitations make them be insufficient to describe complex interaction in real world. For example, the well-known dynamic graph dataset TGBL review and the commonly used text attribute graph dataset books children are both derived from Amazon Product Review Network, which is associated with both the text attributes and the time annotations. However, TGBL review only contains numerical attributes, and the book children ignores all the temporal information. So in this paper, we propose the first dynamic text attribute graph benchmark. We first formally uh, define the dynamic text attribute graphs as illustrated. We define each node is associated with a text which describes the real-world meanings of the entity. For example, introduction of movies or political person's party position. Each edge in dynamic text attribute graph is associated with a time annotation, which indicates the occurring time of this interaction, and a, and a category indicating the interaction type of this edge, and a text description which detailedly describes the interaction. For example, the reviews from users to items are email content. Uh, and our DTGB datasets contains 8 dynamic text attribute graphs from diverse domains. It includes uh, email, temporal knowledge graph, multi-round dialogue, and e-commerce, including both all of small, medium, and large graphs, and both the bipartial and non-bipartial long range and short range dynamic graphs, making it as a comprehensive test bed for this research field. And with DTGB, we design a standard evaluation protocol with 4 critical downstream tasks based on real-world use cases. Expect from the widely studied future link prediction, we dive deeper into 3 more interesting and more challenging tasks, including the destination node retrieval, age classification, and the textual relation generation, which are neglected by previous works. These tasks are fundamental to real-world applications that require the model to handle the temporal evolution of both graph structure and textual information. We have released the codes for training and performing these tasks to accelerate the future-related research. And finally, based on this standard evaluation protocol, we benchmark results on 7 dynamic graph learning methods and 6 large language models. Uh, and our results highlights the performance and the limitations of current methods, including, for example, the scalability issue of memory-based methods, or they neglect the age modeling and the weakness in capturing long range and semantic relevance, offering valuable insights into future attempts to integrate structure and text dynamics. And here, I will introduce each dataset in DTGB. The e-commerce dataset includes Amazon Movies, Google Maps City, and Yelp. All of these 3 datasets are bipartial graph and that describes the interactions between users and items, where items are movie in Amazon Movies, and business in Google Maps City and Yelp. The text description of user nodes are their names, while the text description of item nodes contains its name, category, and description. The age descriptions are reviews from users to items, and the labels are ratings from 1 to 5, indicating very bad, bad, moderate, good, and very good, which user writes the item. Here we give an example of uh, text descriptions and labels in e-commerce datasets. And The second category is the multi-round dialogue dataset, which are extract from the stack exchange data, which contains all user contributed content on various stack exchange sites. It includes both all of the questions, answers, and comments. Here, in our dataset, we extract data from Ubuntu topic and electronic topic, and using users and questions as nodes. And each are discussions from different users on the question posts. Therefore, the text of user nodes contains the name and its self-introductions. For example, their majors, their interests, and their education background. Text of post nodes contains the title and the description of the question, and the each text is the content of user comment on this question during discussion. Based on either one comment is voted as useful by other users in Stack Exchange. We divide the each into categories useful and useless, indicating whether a user can contribute to solving a question. And the third category is temporal graph. It contains the SEWS and GDLT datasets. There are two political knowledge graphs that describe the political behavior across political entities in the real world, such as country and a political person. And the text of nodes are political entities, and we use their sectors and countries and their positions as the text attributes. And the text of each are description of their behavior, such as make a statement. And the age tag category is their interaction types. And the final category is email dataset, where it includes e-room dataset, which is derived from the email communications between employees of e-room company over 3 years. The notes indicate the employees will age our emails along. I gave the distribution of our datasets. We can see that datasets from the same domain have similar distributions. For example, knowledge graph datasets, GDLT, and SEWS both have Gaussian distribution in each text length, and in commerce datasets such as Google Maps City, Amazon Movies, and Yelp show long tail distribution in the number of ages per time step. This demonstrates that our dataset can fit uh, characteristics of data from different domains. And based on this datasets, we benchmark existing methods on 4 tasks, where each classification task and the textual relation generation task are explored by previous works but is essential in real-world applications. Formally, we use data before time t for training and perform these tasks in the future time steps. And we use BERT encoded embeddings based on text attributes of nodes and edges as a row feature of those nodes and edges so as to integrate the text information. Here, the uh, experimental results in future link prediction shows that firstly, we found that simply using portrait embedding to integrate the text information can result in the performance degradation for memory-based models, such as DVREP. And this indicates that we need a more advanced text integration strategy rather than simply use text as features. And then secondly, we found that text information is helpful, especially in the inductive setting, where test nodes are unseen during training, highlighting that the value of text attributes in challenging scenarios such as cold start of recommendation systems. And finally, memory-based methods suffer from high consumptions for large dynamic graphs, especially when long text attributes are included, showing that the necessity of designing more efficient model for joint modeling of dynamic text and structure. And the result in from the destination node retrieval task, we can say that first, although existing models can achieve high accuracy on link prediction, which can achieve more than 95%, they still fail to get satisfactory performance on node retrieval, showing the current dynamic repetition learning methods are far from optimal. Second, existing models perform significantly worse in the historical sampling setting, where the candidate nodes are sampled as the most recently interacted nodes, showcasing that existing models largely rely on capturing structure and temporal occurrences, but ignore the semantic relevance and long-range dependency between graph structure in the graph structure. And the results in the age classification shows that firstly, existing models fail to achieve satisfactory performance on this task, especially on datasets with a large number of categories because of their neglecting of age information modeling. And the text information consistently helps models achieving better performance on each dataset, verifying the necessity of integrating text attributes into age modeling. And here we show the prompt used for textual relation generation task. Here we provide LLM with text of interacted nodes as well as their recent interactions to generate the text description of their future interactions. And the performance on this task shows that, and this task requires a large language model to understand the dynamics and the textual description within a graph structure. We evaluate six large language model on three data sets. We can see that open source LLM such as Mistral and Vicuna perform comparatively well to closed source LLMs in this task, and the supervised fine-tuning helps LLM to get better performance on this task. However, currently, the dynamic graph structure and long-range text history are not incorporated during LLM inference because of the input context length limitations of LLMs. So the current performance is largely no, not optimal, highlighting the requirement of a strategy to effectively incorporating long-range dynamic structure and their detailed text information into LLMs. Yeah, based on the DTGB, in our observations, we think there are many interesting future research directions. Here we give four potential directions. First, with each text description, we can do controlled textual relation generation. For example, we ask LM to help a user to generate review for restaurant that mostly talk about its environment. So this requires LLM to extract the recent reviews from the dynamic text attribute graph about its environment description. And the second, as we mentioned before, we need a method to effectively incorporate dynamic structure as well as long text context to LLMs for dynamic graph reasoning. And we think one strategy is to design the temporal graph tokens, where we first use the dynamic graph neural networks to embed the text information and the structure information of dynamic graphs, and we use this token. Uh, we integrate this token into LLMs to uh, integrate the dynamic graph information. And third, given the long text description associated with nodes and edges, as well as the long historical structure, how to efficiently modeling their semantic and structure convolution to get dynamic nodes and edge embeddings with higher quality is a interesting task, which is also very valuable for many downstream tasks for dynamic text attribute graphs. And finally, giving the rich text and time-related information, using LLMs to do temporal question answering and evolution summarization is also interesting. For example, giving the email or discussion history among users, using LLM to summarize the development of their conversation and question answering about their discussion is also an interesting direction. Uh, yeah, thanks.
Thank you very much. I think that was the end of the slides, right?
Yeah.
Okay. Thank you very much for the great presentation. If anyone has any question, please feel free to unmute yourself or ask it in the chat. I just wanted to ask one question about you mentioned that the future direction is to have some method that somehow integrate the LLM or the uh, temporal graph models, but do you have any kind of um, result on those kind of models right now, or um, the text attribute generation and the model training is completely separate process?
Actually, this currently there are many models that can integrate the static graph into LLM, but integrating dynamic graphs into LLM is it's still unexplored, and it's have several key challenges compared with static graphs. The first one is that for dynamic graphs, it's important to understand and describe the evolution of nodes and the history of nodes. So compared with static graph, we need to uh, this token need to not only understand the graph structure, but the evolution history of nodes. And the second is the efficiency problem. Say, as we just show that many existing dynamic graph neural networks are suffer from high time consumption and OM problem in large graphs. So if we want to use LLM to do query and answering on some generation on large language models, we need a efficient model that can encode the long run history so that LLM can know more about the graph structure. And also there can be another interesting direction is that we not use the graph tokens to integrate dynamic graph information. We can use some graph retrieval to integrate dynamic graph information into LLMs. Say we have text attributes of these nodes, and we can first use LLM to retrieval on dynamic graph to retrieve some temporal passes or temporal subgraphs. And then we summarize the text descriptions of these subgraphs or these passes and use them as augmentation for the reasoning or for the generation of large language models.
Yeah, that makes sense. That is very interesting, and I'm sure that all of these data sets would be very valuable for the community.
Hi. Uh, Thank you for the really interesting talk. If I understood correctly, the DTGB dataset benchmark you are proposing offer a temporal network with attributed graphs. But my question is, do you handle dynamic attributes? So if you think to, for instance, the Erden datasets in which you have two users, and when a user send an email to another user, you exchange an email, and the content of the email is on the edge, right? But my question is, do you also model dynamic attributes? So just to give you an example of what I meant is, suppose that you have a face-to-face interaction network among people. So of course, the topology of the network is going to change over time because people, talk with other people and this kind of stuff. But the attributes of the node may change over time. For instance, going back to the face-to-face interaction network, a user today may be happy and tomorrow can be sad, for instance, or can have another, let's say, another emotion. So in this sense, does your benchmark also have dataset in which the node attributes change over time?
Yeah, thank you for your question. This is a future, interesting question, and this is a future direction of our this benchmark data set. See, as you mentioned, in our data set, the dynamic is mostly in the age level. See, with the time evolving ages, different age has different time descriptions, and the nodes has the same the text description. But yes, so in some cases, the description of nodes will also evolve over time. So it's interesting to collect data sets for these domains. And I thought another more interesting is that maybe we can uh, not just concentrate on the text attributes. Say for nodes, it may have some weights, uh, say time series. Say they are
Yeah.
ages have nodes have time series features attributes, and this time series may also in related to the temporal interaction between nodes and their uh, interaction test descriptions. So yeah, we thought we can do this in the future works.
Yeah. Thank you. I think, yeah, I agree with you. I think it will be really interesting to have not only the dynamic of the topology and the information on dynamic edges, but also taking into account the dynamics of the state of the nodes. So the easiest example is I don't know, the feeling of people in a face-to-face interaction or this kind of stuff. But thank you for the answer.
I have another question. Um, so are you aware of other benchmark data sets that has some like similar structure as your benchmark, but maybe it's not for general dynamic text attributed graphs, but maybe for specific domains such as recommendation, um, with these text attributes? Like, are you aware of any of these other data sets?
Uh, Actually, I aware of another data set also accepted by Europe's 2024 is uh, TEG. I thought it is another text attribute graphs as with age text. Yeah, but they ignore the temporal information. And
I
for
see.
dynamic, yeah, and for dynamic graphs, uh, as far as I know, most existing data sets may contain some text features which are derived from the raw text, say bag of words or something. They just provide these statical features, but none of them provide the raw text of the nodes and apes.
I see. Thank you. Can you remind me the name of the NeurIPS dataset paper?
I remember
The
it's
other one.
TTG.
Oh, okay. TEG. Got it. Thank you.
So if we do not have any more questions, I would say thank you very much for the interesting presentation. And I think that's it from our side, right?
Okay,
Thank you very much.
thank you.
Thank you.
Thank you. Bye bye.
Bye.
Bye.